Hello, everyone, and welcome to the Switch Statement Podcast. It's a podcast for investigations into miscellaneous tech topics.
This is our 11th episode on Godel, Escher, Bach by Douglas Hofstadter.
Hey, John, how you doing?
Hey, Matt, I'm doing well. How are you doing?
I am doing all right. I'm ready to just dive in, bare-chested into this whirlwind tour of discrete mathematics and logic.
I feel like this is even more the deep end than this series has already been. Like, this book already feels like every single sentence and paragraph can be analyzed infinitely. And now we are taking three chapters and trying to do some episodes about those three chapters. Like, it's going to be tough.
I mean, I'm ready for Douglas Hofstadter to say, oh, now read the whole book backwards, and that's actually a whole other thing about some other cool topic. Yeah, man.
That wouldn't surprise me at all if the book itself was structurally, had some. He had a joke about that. I think it was in the last chapter of the three, or no, it was in typographical number theory, where basically the whole entire dialogue. Wait, is that what the things are called? Dialogues?
Yeah, I think they call them dialogues, yeah.
The whole entire dialogue was palindromic conceptually and also literally. A lot of the sentences were the same. And he made a joke I couldn't believe it when I noticed that I had written this palindrome. It's obvious that he spent hours and hours piecing this thing together. So I thought that was funny.
I feel like I picked up pretty early on. There was this weird transition between the two, and it's okay, there's something stilted, and it's you just start to read the last few sentences the other way, and it's okay, it's one of those backwards and forwards things. But so this episode, we're doing things slightly differently, or we're what we realize is I think there's a ton in this book, and if we do everything at the finest level of detail, we will be spending kind of an infinite amount of time doing it. So we're gonna cover what's that?
I think it's almost better for us to cover this at a higher level too, because for one thing, if you're interested in this material, you should read this book. I think this book is very I don't know. It's kind of an amazing book.
To call it a book is almost not correct. It's because it's there's exercises in there. It's kind of a cross between a novel and a textbook, basically.
It is, and it's also so unique in its, or at least from books I've read, it's so unique in that it is I want to say meta, or maybe interdisciplinary is a better word. Yeah. Where, a lot of the book is talking about logic and math, and this chapter is called propositional calculus, I think. But it's also talks about music and talks about just thinking, and there was a whole chapter about Zen and how that sort of ties in with Gödel's incompleteness. And it's just kind of this book that's simultaneously insane, but also highly dense with knowledge and these amazing sort of logical nuggets. So I don't know, it's a very cool read. It's very different from most reading experiences, I would say.
Oh yeah. But so these chapters we're going over chapters 7 and 8, and this is the propositional calculus and typographical number theory. And it's funny because to your point, it feels up until this point, while we were reading them, it felt super dense and super tough.
Yeah.
And we get to these chapters, and it's oh, okay, those were all toys. Those were all little, play school things, so that we can, our brains were primed for, the actual knowledge that he's trying to dispense.
Yeah, we've shifted into overdrive. It's he's described how formal systems work, and now he's telling us, this is the formal system that represents human knowledge, which is this kind of crazy leap. And then you start to see the power of why... who are the two guys who wrote the Principia Mathematica.
Russell and Whitehead, I think.
Yeah, like why Russell and Whitehead and so many mathematicians of that era were so obsessed with this concept, because it's so incredibly powerful to be able to represent knowledge with, symbols and formulas, and then be able to like basically generate new knowledge by applying existing rules to those theorems, basically.
And that's exactly what he does here. What Hofstadter does here is and with these 2 chapters, like kind of by the end of the second chapter, we wind up with a system that is equivalently expressive, is my understanding, to the system that Principia Mathematica laid out.
Right. Yeah. And he does a few exercises with the system, one of which was kind of funny, where he's trying to figure out whether this guy Ganto will chop off these monks' heads.
I hated this so much, dude. I'm just going to come out and say I hated this so much.
That's fair. Yeah, no, it was kind of idiotic, but it was also kind of awesome because he basically used this logical system to deduce that Ganto was like about to chop these monks' heads off, and I just found it amusing.
Well, let's. I should have the thing up here.
Nice.
Let me see if I can read this out. So this is a Zen koan, which we're gonna get into a lot more detail in the next episode. But so it says, one day Toku-san told his student Ganto, "I have 2 monks who have been here for many years. Go and examine them." Ganto picked up an axe and went to the hut where the 2 monks were meditating. He raised the axe, saying, "If you say a word, I will cut off your heads. And if you do not say a word, I will also cut off your heads." Okay. And so of course, Hofstadter breaks that down into a series of logical statements. And he's expressing it in this kind of proto system before we get to his typographical number theory, is it?
Right.
And so, like, obviously, our what is it, like, intelligent mode mind is saying, like, okay, well, it doesn't matter whether or not they speak. The reality is, like, he's going to cut off their heads. But so, like, the conclusion is both monks continued their meditation as if he had not spoken. Ganto dropped the axe and said, "You are true Zen students." He returned to Toku-san and related the incident. "I see your side well," whatever, blah, blah, blah. So anyway, he does not cut off their heads. It's like...
Yeah. It's like you had to cut off their heads based on propositional calculus.
Yeah, it's like, aren't you being... Like, you're supposed to be completely consistent. But, yeah. I mean... I guess not.
But yeah, my take on propositional calculus was sort of this introduction of building logical sentences from scratch that basically contain truth. And typographical number theory was almost like a full, rigorous definition of a system that uses numbers. And I guess I guess it still used symbols, but it was like you could do math on these like numbers, do math on these symbols.
Basically.
Yeah, exactly. Which are called theorems, I guess.
Yeah. Or there was another word they used, which was, I think, formulas.
Formulas.
Which they're equivalent, though.
Right. And he introduced a couple new symbols for the typographical number theory to represent things like for all... Like you could say something like for all x plus 0 equals x, which is kind of a trivially true thing. But he just introduced these new symbols so that you could represent that statement very tersely.
It's interesting. Yeah, so in the first chapter, he kind of just lays out like and, not, or, and then also like implies relationship. So you can basically, he sets up the framework where it says like, okay, you can make an expression like if X is true, then Y is true. And that's kind of like the core of the, of the propositional calculus. He also provides a way to like prove one of those statements, like assume X, like, and then I'm going to show you that this other thing is true. And then he allows you to kind of like come back from that hypothetical world, and this goes back to the pushing and popping.
Yes,
yeah. Go for it.
I was just gonna say I had not seen that. I thought that was very interesting. Like, I want to say he called it maybe the fantasy rule and the carryover rule, where basically you'd start with a logical premise, and then just like you're saying, you'd sort of push into like a nested set of statements. But within those nested set of statements, you could carry over any of the logical premises from like the outside, the outside world. And in this way, you can sort of like, do a little bit of logical deduction based on something you've already proven, and then pop back out and like use that final logical deduction, within the outside world as well. So it was kind of this way that you can like get deeper and deeper into knowledge, but then apply that knowledge.
Yeah, it's funny because as you're reading this so much, like, it's funny because there's kind of a chicken and egg question, like which came first? Is he deriving inspiration from computer science, or is it vice versa? Is computer science kind of like, because so much of this feels familiar, like it's just a function. You like
Right.
You have a thing in there, you have in this outer scope. You can reference it, and then you can kind of return something back from it. And so, it's and I just don't know, because this book was written like in 1979 or something. So like before most of the modern programming languages were already written. So
it also introduces this other concept that I don't know if he like explicitly stated this anywhere, but I feel like the mental leap made sense to me because of so many of the other things he's talked about. Like, for instance, he talked briefly about chess and how you can, or maybe he just talked about like game systems, but basically in chess, you can take an existing chess position and you can determine all the legal moves and just sort of apply all of those legal moves to get any of the next chess positions.
right.
Similarly to how you can take some piece of knowledge with propositional calculus and apply any of the known rules and get like a new piece of knowledge that may or may not be some like novel piece of knowledge that's, completely unknown. And it's very reminiscent of Euclid's Elements, which was also touched on in this book, where Euclid sort of started with these, I think it was 5 postulates, and then like built the entirety of geometry using only those 5 postulates and basically pushing deeper and deeper into like a logical deductive reasoning. And it's just, I don't know, like it struck me as this amazing idea that if you have a formal system and a set of rules for working with statements in that system, you can almost like generate new knowledge by just applying these rules to existing statements.
But and we're going to touch on this a little bit in the next episode, but isn't that still true with the system that we already have? Like this whole book is really a way to understand Gödel's theory of incompleteness. And like, I don't know if that was really clear to me at the outset. I know he talked a lot about that.
Yeah.
But the singular purpose is really that the reader understands Gödel's theory of incompleteness. So, but it's unclear to me, like, can't you still do that same thing with the current system and like find new, like, the only thing that Gödel's theory of incompleteness says is that there are some statements that are true that aren't theorems in the system.
Right.
But aren't there still, like, given that we can express a bunch of these like useful mathematical constructs, like, can't we still do that search and find useful mathematical things?
Yeah, well, and that's what I am finding funny about this book is this book is almost each chapter has like a basic formula where like he introduces some premise, like it might be a logical framework, and then towards the end of the chapter he'll sort of talk about how the premise breaks down. Sort of these cracks in the armor of like logic and reasoning. But when I'm reading about these logic and reasoning tools, I'm just sort of seeing how useful they are. And I think that maybe this is because I am a programmer where, in programming, there's just so much it's hard to explain, but in programming, there's just so much jank. Like if you're working in like a large software system, you're so used to seeing these like nice little nuggets of code that are kind of perfect and functional, and like they feel like they perfectly capture the model of a problem, and it's sort of this really elegant thing. But then there's also these other parts of the code that are just like duct taped together garbage. And you're just sort of used to these systems that have both perfection and jank simultaneously.
Well, yeah, it's like all of computing is these like beautiful pieces of code that have been like just completely jerry-rigged and duct taped together.
Right.
To actually like get something real done. Because like just with that beautiful like isolated thing, like you can't actually do anything that useful.
Yeah, dude, and I'm so glad. I feel like those words you used are so perfect because it's almost like making something useful by definition is like an interruption of perfection. It's like it's
Dude,
like
talk to Haskell programmers.
Right. Well, and that's another thing in programming that I always find amusing is every programmer feels like there's this ideal way of doing something. And, when you sit down to like work on a problem, like that's what you're trying to achieve is this ideal thing. But there's always this threshold where you break it, and for some programmers, like I'm a pretty mediocre programmer. So my threshold is like, pretty soon into my workday, I start breaking down and doing things that are suboptimal. I think some programmers can get much further in their workday where everything is utterly elegant, but there's even a point where they break down. And yeah, it's kind of like what you're saying. It's like if you want to do something useful, like something's going to be janky.
It's all a spectrum. Yeah, and like I've worked with programmers who they really feel and I'm more on this side, I would say. Like they really need to fully consume the universe before they start working on their apple pie. Like they just I'm kind of mixing metaphors here, but before they can take a step, they need to really understand like the full system. And I don't know, I'm like I can get like that sometimes, but yeah. I fight that urge, or I try to at least.
Well, and this is one of the things I love about working with you is I think we do occupy two, fairly different spots on that spectrum. But I think both of us are still far into the zone of like practicality. Like we're both pragmatic at heart. Which I think is also important because I think you can also reach a point where you're just no longer being practical. Like you're chasing perfection to the extent that it's not productive.
Right, exactly. Just like Russell and Whitehead with their Principia Mathematica, and Godel had to come along and say that, stop it. There's no perfection. One thing I did want to talk about is actually induction, just because like it's a personal, like I think is really cool. Mm-hmm. So they raised this issue where the system is able to, you can kind of infinitely generate all of these rules from the rules. Like you can generate any like 0 plus some number equals that number. Like you can generate that all day long. And then as an intelligent person, you can look at that and you can be like, oh, okay, well, it can generate any number. But then Hofstadter kind of raises a red flag and says, well, it's important to note that like you're kind of stepping outside of the system. Mm-hmm. You're just using your intelligent mind to do that. And but what you really want is something where the string itself, and you talked about these quantifiers, there's this universal quantifier which says like for every number, right, X, this thing is true. And the system can't do that as it currently stands, even though you could generate all of them. And we actually need this special trick of induction. So if you've never taken like a logic class, the way that it works is if you can prove it for the base case, which is like 0 in all these things, and you can prove for like a hypothetical x and x plus 1,
Right.
then you know it to be true for all numbers, because like and you think of it like a ladder, like that's always the metaphor, where it's like all you need to prove is that like you can take one rung and the bottom rung is there, and then you know it's true for all numbers.
Right. Yeah.
Which, I don't know, it's just a very powerful tool.
Absolutely. Yeah. Very cool. But yeah, maybe we take a break at this point, because I feel like we've sort of set the stage. And next we'll talk about how formal systems can be mapped back to typographical number theory, which is a very powerful concept. And we'll also talk about Zen.
Talk about Zen. Yeah, take a little Zen, a moment of Zen in this book. So, all right. Well, I will see you there next time.
See you next time, Matt.